So yeah, good afternoon. This is our third week lecture, and so we're gonna move on to generalizing Kullback-Leibler law and discuss projection using Bregman divergence. And recall that theta is the parameterization. So this is basically E flat E geodesic, right? Space. And then this precise theta turns out to be a very important function that characterize the moment, right? And so so then one coordinate system. So here we characterize distribution in terms of theta, but you can actually characterize distribution in terms of another parameter, eta, which is basically this one, right? I mean, and so there's so theta is in this case is called natural or canonical parameter, and eta is a dual parameter or expectation parameter. And so Bregman divergence is defined. By the way, did I record it? Okay, I think I recorded. So, so Bregman divergence is defined something like this. So, so first of all, you notice that it is derived from psi. So basically, this guy characterize the distribution and also the divergence, and then later we will call this one as a generator, because this one indeed generate a space coordinate system. And so if you look at, so the meaning is, given psi theta, we have a tangent, right? So this is basically you linearize, and so this is psi theta, and this is actually psi theta null plus derivative theta null, and then times theta minus theta null, right? And so this is actually a linear space. And so the difference in the tangent line basically will because of the convexity, right? Because this psi is a convex function, then that means we will have this inequality. Okay. And so okay. So then in the special, so this one doesn't so this one is actually defined using only psi, right? So it doesn't really have to be an exponential family. But in the special case of exponential family, turns out that this Kullback-Leibler divergence is equal to Bregman divergence because of we actually have this equality 4, and so
This Bregman divergence is defined for general convex function.
yeah, right. For any convex function, strictly that has to be strictly convex. Yeah. And so this is definition, right? This is definition of Kullback-Leibler, and this is the property that we can derive from Kullback-Leibler. So let's take a look how we can obtain this equality. So this is the KL, right? So this is KL, and then force equality is basically exponential family. in 1, right? So in the exponential family, in equation 1 here, the difference, basically this is theta, right? And so exponential log of this guy is just the linear in theta. So basically we'll get something like this. And then now the integration is involved with the density function. So then this guy can go outside, and then this is just the expectation evaluated as theta prime, right? And then the remaining part is just this one, because F is density. And so then if you and then so this is basically is a definition of expectation. Expectation of px. So actually this is not really correct, because this guy should be expected theta prime of px. Sorry about that. And then this guy is by this property, equation 3, right? So you by this property you can write it as a tangent. I mean derivative. So then you can express it in terms of the as a Bregman divergence. Okay, and then you can notice that we actually have reversed. The order is reversed because because actually because the in the characterization of distribution, this psi has a negative sign. So that's why it's reversed. Okay. Now we can formally define dual function, how we can understand the duality. And so this is called Legendre transformation. So this is very interesting and intriguing idea, but turns out that it's very powerful idea. So basically, this is just given, right? Okay, given eta. Well, actually, no, the other way around. So this is given, right? Psi is given. So psi is a function defined on theta space. So psi theta is kind of fixed. And then we apply this operation, theta times eta, and then take the supremum, and then supremum over theta, and then it's a function of eta only, right? Okay. So then that's why we it's a function of eta only here, and then let's call it phi. Okay. So how we understand this? Well, first of all, because this is a supremum, right? So that means that given for fixed eta, this one will be less than theta and eta minus psi theta, right? For all theta, for any theta, because of definition of supremum. And so which means that we will have this one, right? Which will imply, uh, so will imply this one. Okay, so now that then the question is, when we have this inequality reduced to equality, that's when theta is chosen to be the supremum, the value achieving the supremum, right? And so that means that theta, so if you choose theta star to be the one that achieves the supremum, then we'll have I mean, that's the kind of definition already. So we'll have equality, and then the equation that characterizes the supremum is essentially boundary. I mean, right? So then if you write the whole this function right? So this function differentiate. So this is called the first order condition. So necessary condition. So the supremum, the point at the supremum will satisfy this equation, right? So that means we will have this one. Okay. And then this inequality here will be called Fanshawe-Young inequality. And the equality condition is this one. Okay. And now, if you look at this inequality carefully, then actually that's a symmetric, right? You can just exchange the notation. So you can actually call psi as phi and call phi as psi and apply the same argument, right? Then you can get, basically you can apply the symmetry. That means the equality will also hold in terms of this equation. Okay. So basically this equation and these equations are equivalent because the function, the way the function is. So basically is, you can think of it this way. So there's a, space of, so we have a space of distribution, right? So we have a space of distribution, but the coordinate system here, the coordinate system here is in terms of theta, left side. The right side, the coordinate system is eta, right? And so basically the same distribution can be located in a different way. So turns out same one. So say particular P0 can be located here in this theta space, theta coordinate system, or can be expressed in terms of eta, right? Then the way there should be a formula for bridge, right? So how do we translate from one basically language, right? I mean, from one language to another language. How do you want to translate this equation, right? So basically, equation 6 it translates from theta to eta, and then equation 7 translate from eta to theta. So equations 6 and 7 shows a dualistic structure concerning the two coupled coordinate systems, eta and theta and eta. So then these two are actually representing the same function in a different way. So the connection is something called Legendre transformation. And
so this 6 and 7, I guess, will only hold at the optimum value of theta star, right? Will only hold under this condition at theta star.
okay.
Right?
Uh,
question that like this 6 and 7
okay.
will only hold when theta is equal to theta star. That means if this equality holds in equation 5, then we can write down equation 6 and 7, please. Right?
Yeah, so equality in equation 5 will hold when 6 hold, which is actually same as 7 hold. Okay.
6 and 7 basically depends on the equality of 5.
Yeah, so that is a condition for achieving the equality. Okay. And so this is a very intriguing idea. And basically, so how do you want to express a particular function? So one way is XY coordinate system, right? You can express characterize your particular function in the XY coordinate system. That's one way. Another way is like a P and intercept. So P is a tangent. So okay, you can think of a line. So you vary P, you change P over, okay, and then basically for each P you find out the maximum intercept, maximum value that so that X star. I mean, so then at this one, this the value of intercept. So that is intercept. So that right. This is the basically intercept, the difference between the zero, the line between the line and original function is maximized at x prime. So that means this f star. So basically, see here we have x and fx, right? So that's one coordinate, one way to write function, x and fx. The other one is p and f star p, right? So that is a dual. So yeah, so I think yeah. So basically, the functional relationship specified f can be represented equally as a set of xy point or a set of tangent lines specify their slope and intercept values. I mean the intercept at the maximum point. Okay. Now, okay, this is another result. So we have psi is a strictly convex and second differentiable, and then this is a transformation, right? I mean duality transformation, and then turns out that the Hessian of a dual function is a inverse of the original Hessian of the original function psi. Okay, so that is the Hessian duality. And here's a proof. So the legendary duality is this one, right? So legendary duality is eta is a derivative of psi, and theta is a derivative of phi at eta. And so that means we can actually insert this guy into here, right? You can insert this guy into the second equation, then you obtain basically identity result. So that is identity function basically. And so you now want to take a differentiation both sides with respect to theta, okay, and apply chain rule. So then that means this is here. This is, you can write it as a g of f theta equal to theta, right? So you can write g of f of theta is equal to theta, and then take the differentiation with respect to theta at both sides. So then, first of all, the chain rule says that the differentiation operation will be something like this, right? That's chain rule. And then because this is identity function, we'll have this identity. So that means then now, so we have only to evaluate what that means, and which is not difficult because basically G, okay, f theta. So this is f theta, right? F theta. And so derivative of psi, I don't know. I mean, yeah, it's just a notation. Uh, psi phi. I mean, uh, nebula phi of nebula, right? Is this one. And then this guy is what? Psi zeta, right? And so you get this one. So that means uh you- basically this identity using chain rule is just this one. So that means you obtain this result. Okay. So that is about Hessian duality. And so the duality basically create this mapping summary. So you have a dual coordinate system, right? And then convex conjugate function, basically this phi eta is a supremum of zeta eta minus psi zeta. And of course, uh, so so psi, I mean, phi is a convex conjugate function of phi, psi, and then psi is a convex conjugate function of phi, right? So they are convex conjugate to each other. And then uh, Hessian, right? So remember that the metric is metric associated with zeta system is G zeta, right? I mean, so this is the actually the metric, and so let me see. Where did we cover? I think we covered in the first last semester. We lecture 1 or lecture 2?
Lecture 1.
Right. Okay. Yeah. So somewhere.
Local metric. Yeah.
Yeah, I think in the very beginning, I think. Yeah, let's see. Thank you. Yeah, something like that. So metric, right? Okay. Right here. Somewhere. Mm, that's right. Score. A. So Fisher information, I mean, in the exponential family, right, right. Yeah. Let's, sure, right. Okay. Well, uh, at least, yeah. I think, yeah, that's right. So we, yeah, because the definition, that's right. In the case of exponential family, then the then Hessian, right? I mean, yeah, I think this already you know, so because this in well if you this is actually variance covariance of so you can view it as a covariance of S1, Si, and Sj, but also you can view it as a Pi X and Bjx, right? The subinstance statistic. Okay. But this is for the exponential family, and actually for the for our case we do not necessarily also exponential family. So then this is indeed the definition of a metric. Okay. So I guess yeah. So if you if you Bregman divergence, so if you view Bregman divergence of psi, and then this is so Hessian of Bregman divergence is indeed because this is just linear, right? Linear in zeta. So if you take the second partial, you know, second order differentiation, you have just this one, right? Okay. And then the dual function has an inverse because of the Hessian duality. Okay. And now let's use the duality to express Bregman divergence. So if you, okay, so we have a one coordinate system and the other one is another. So zeta and eta, right? And now, so here in zeta we have a psi, and eta we have a phi eta as a potential function, right? A generator function. So then we can actually use that to construct the Bregman divergence, which is this one. Okay, so this is the Bregman divergence. It's the same way we use exactly the same formula here, right? So this is the formula in the zeta coordinate system. In the zeta coordinate system, psi is the generator. And now in the eta coordinate system, phi is the generator. But the phi is should be the convex conjugate function. And so that means now let's try to understand between the relationship between the two. So this is interesting because okay, so using 5. So 5 is what? This one. Okay. So we this is for any, right? This equation 5 it has an inequality, and in this inequality, this is for any for any combination of eta and zeta. But if we choose eta to satisfy to the this functional relationship, 6, right? 6 and 7. If you choose this condition, boundary condition, then we have an equality. And so we can actually, so this is the basically equality situation. So this is equal. If what? If psi, okay, eta equals zeta, right? So in that case, we have equality. And same way, this one, same way, we'll have this equality. Okay. And same way, we'll have equality. Right? So that is the first equality. And then there's a cancellation. The cancellation occurs when we have, oops, not this one. So where? Okay. So, okay. Now let's take, so the first equality was checked. Now let's check the second equality. The second one, so this guy moves to here. This guy just written here. And then this guy is equal to eta. Okay. And then I think we have some cancellation. Okay, right. This guy. Okay. And so we finally have this result, equality. And then after that, it turns out that this is nothing but Bregman divergence in terms of zeta coordinate system. So there's a very nice, beautiful, I mean, so whatever distance, right, between the 2 points in one coordinate system can be matched to the other system as long as we use the same, convex conjugate. So as long as the generator convex conjugate to each other, basically, right? So that is basically what this is about. But the difference is that the order is changed, right? So the orders are changed. So that is okay. So the dual divergence is equal to the primary one if the order of 2 points is exchanged. So that's basically is okay. So the divergence derived from the two convex functions are essentially the same except for the order. Okay. So Fenchel Young gap as Bregman divergence. Okay. So this is for any. So now we have a 2 point P and Q. Okay, P and Q, and so P and Q. So P can be located either can be written in the zeta coordinate system, also in the eta coordinate system, right? And so let's say zeta P is a value coordinate of zeta in zeta coordinate system, right? Eta Q is the coordinate of Q in eta coordinate system. So first of all, okay, let's first express so this is the definition of a Bregman divergence. The definition of Bregman divergence will have the first equality, right? So that is for the 2 point, we'll have the this first equality. And now this guy is equal to eta Q. by the definition of you know, dual mapping. So this is eta q. So that means we can write, and then what? Then we use this guy is a psi q. Oh, no, eta q, theta q, theta q, eta q. I mean the order, the order doesn't make a difference, but okay, to be more rigorous, theta q, eta q minus psi theta q, right? Okay, yeah.
Eta q have to be defined as the gradient of eta q. Is it have to be crossed? I mean, eta q is defined as a gradient of theta p.
Eta q, okay. You mean the here?
Lemma, therefore, above, when we first
This one?
above, one line above.
This one? Ah, yeah. Well, with the equality. I see, that's good point. With the equality. So this is, okay. So this is equality no matter what. Okay. This is equal no matter what. But now this guy, so this guy is, of course, this is because this is divergence, Bregman divergence. It has to be non-negative. Now the question is when they are this inequality leads to equality. That's only when P is equal to Q, essentially. At least the P and Q are equal in the coordinate system. Okay, so that's basically what it is. So yeah, that's a good point. So actually, see this guy, the definition of this guy is eta P, right? So this, but our question is when with the equality if eta Q is equal to eta P. Okay. So that is basically so the proof itself is not that difficult, I think, but there's so many new concepts, so maybe it may take time to get familiarized.
So it's just essentially saying good equality depend only the p and
Is
Q
Q.
same point.
Yeah, that's right. Okay, that's right. So I think yeah. Yeah, it's not really new, I'd say, but some sense. Okay, now we the goal eventually we wish to establish Pythagorean theorem for the Bregman divergence, right? And so then we we want to use this inequality equality to for the 3 point. And so for the 3 point, okay, for any 3 point, you can actually write down. So do some algebra, right? Do some algebra and then simplify, and then end of the day, you get something like this. So now our ultimate goal is to want to show that this is zero, right? So this is what we really want to do. And so once we can show that, then we are happy, right? We have a Pythagorean theorem for the Bregman divergence. Okay. So well, so the bottom line is we need some kind of a dual flat. So flat. remember when we talk about projection, last time, week one, there's a M flat, E flat, right? So basically, what do you mean by flat? It's a kind of a linear affine space. So basically, the condition that we want to impose is this guy belongs to one line, and this guy belongs to another line, right? And then we need some sort of and then we want to check that the you know inner product is zero. So that means we need some sort of dual affine coordinate system. So affine means linear, right? So so basically we want to do some sort of a geodesic line. We want to create a line. And so given the so the initial, because we want to have this Q, the overlapping line point should be Q, and we want to make it like a P and Q and R, right? And so then starting point is Q. Just the one is in theta system, the other one is in eta system. And then this is a line. Okay. So this is basically a line connecting P and Q. So first line is a theta line connecting P and Q. Second line is a line. Second one is the line connecting Q and R, right? And then T is like a geodesic. Yeah. I mean, T is the line. So curve. So two curves are said to be intersect orthogonally when their tangent vectors are orthogonal, right? Remember. So that means we need this inner product to be equal to zero. But this inner product in this geodesic line, in the information geometry, should involve this Gij, which is the metric, right? Remember, we need to, I think here, yeah, metric. So when you define two vectors, inner product of two vectors, that actually involves G, which is this one. So then we want to show that this is equal to zero at t equals zero. Okay, but we want to make sure that these two lines actually intersect at t equals zero, right? And so notice that if you by construction, if we set t equals zero, then this guy is a theta q, the other one is eta q. Okay, and theta q and eta q represent the same point in a different coordinate system. Okay, so here's a generalized Pythagorean theorem. So PQR in a dually flat manifold, and we call this triangle an orthogonal triangle if the dual geodesic connecting P and Q is orthogonal to the geodesic connecting Q and R in the sense of 11. And then in that case, we can achieve this Pythagorean theorem. So we need to more clarify what I mean by this orthogonal here. And so basically in the proof, okay, so recall the equality in 10. So it's equal 10 is a 3-point equality, right? So remember that we have a 3-point equality. No, right, this one. 3-point equality. And then show our goal is to show the cross term here is vanishes, is 0. So remember, we construct this line already, right? We constructed this zeta geodesic and eta geodesic line already. So the tangent line, the slope is essentially zeta p minus q, zeta q, for the zeta geodesic, and then in the eta geodesic, this is eta p and q minus eta q. So to make the this term equation 13 0 from orthogonality, we make explicit how the inner product in 11. So okay. So basically here this is a goal, right? I mean, still this is goal. This is what we want to show. Well, no, actually this is assumption, because we want to assume orthogonality in the beginning, and then basically show that this orthogonality implies this guy is 0. Okay, so because otherwise we need to assume something, otherwise we cannot really say orthogonality, right? So but easiest way is to assume this guy is 0, but that's doesn't really means anything. So we really want to start with 11. Okay, start with 11, saying that okay, let's assume that this is true, this is 0 at t equals 0. Okay, and then see how that can be expressed in terms of our dually flat geodesic coordinate system. Okay, it turns out that there's some, because of this duality relationship, we can kind of establish this. Okay, you can just I guess you can just take a differentiation, right? So d eta is it's like okay, d eta. How do you differentiate? So okay, maybe this way. D eta d zeta is nebula square psi zeta, right? From here we can obtain this. So that means this is actually G, right? So that we obtain this. Okay. So because of this, we can say that this guy is actually G inverse, because it's inverse. Okay. Something like that. And then this guy is this guy. So we actually this Riemann inner product, right? Riemann inner product at Q, it can be written as something like this. Because this guy and this is metric, and this is vectors, right? So this guy is this vector, and this guy is this vector, and then we have a metric. Let me say it again. So this is essentially a definition, right? I mean, how you define this inner product using a metric G. So you have this guy, and this is one vector. This is another vector. Okay. And so we and in the end we get this. So but because we set this one is 0, right? As an assumption, that means this term will be 0. Okay. So that gives our proof of the Pythagorean theorem. So yeah, I don't know whether this is helpful, but basically this one, this is the orthogonality condition. But tricky part is we originally this QP 0, oops, QP 0 and zeta dot QR 0, not 0. G zeta Q. Okay, so that is inner product, but turns out that this guy, it can be written as a language of eta. Okay, and then this G turns out cancels to each other. Okay, I think we can have a short break, maybe 5 minutes, and then move on. Okay, so now we don't really have to use zeta and eta notation here. We can just directly use P and Q as a component, and G is a general, basically generator convex function that create the Bregman divergence. So then the definition of Bregman divergence is now something like this. So remember, if we choose this one, choose this particular one, then you can actually work out the definition. So P, right? P of G and Q, G of Q, and this is the derivative, right? This guy, and P minus Q, and then integration. The inner product is just the integration. Okay, and then then we have a sum cancellation. This guy, this cancels with this, and so and then also this one is just constant, so it goes away. So then only this one left, right? And so which is basically this one. And so you have something like this, which is actually Kullback-Leibler. Yeah, sure.
So here, PQ represents the real vector or kind, I think it's the probability.
So P, yeah, right. Space, look at the space is a distribution.
So
Okay, any element in P.
we have to derivate with regard to P or Q here. No?
Yeah, right.
Functional derivative. Yeah,
Huh?
functional derivative.
Functional derivative. I see. Right. Functional derivative. So I see you. I know. Okay. Well,
If it is identifiable, we can change to the parameter and the same thing.
right. I think I see your point. Okay. So your question is what exactly this
What
is.
set objects? What is the argument here? How to derivative? Because I'm not familiar with the function of them.
I see. Well, that's a good question.
It is In week two, some appendix. Week two appendix has the technical details of functional derivative. Your slide in week two.
Week 2, okay,
Can check.
okay. You mean, I see, I see. Actually, you mean this one, kato, this one, kato derivative,
That is church functional derivative.
okay,
form.
okay, yeah. Right, I think there's some details, okay, right. So here, suppose with this, right, so we have a certain directional derivative, right? But I think in many problems you can just assume you have a discrete distribution, right? And then just apply. That seems to work, but there may be some more, rigorous details that I didn't cover. That's right. Okay. So dual coordinate. So that is basically you it's like this. Okay. So remember psi theta. Oops. So we already have this, right? So eta is a dual coordinate of theta, right? And but now the argument here is a G and P or Q, right? So then it's still the same thing. So this is actually okay. So basically Q, if your Q is a subspace, so this is a dual coordinate. If you, I mean, well, there's no, we don't really have to consider this one, but just this one. This one in itself, because you move Q over, right? You move Q over, then whatever the space that it generate is a dual coordinate system. Okay. And now affine. So we first introduce dual coordinate and then affine sets in dual coordinate. So affine means that you now have a subspace, which is affine, linear. And then along that space, you move Q over, and then like this, right? You have a Q in particular, like a M flat. Okay, you have a big M flat. So suppose your model is something like expectation of Q over Tx is a C, right? Something like that. So this is space, for example. So you can actually move. So see, if Q1 and Q2 belongs to Q, then it's linear, right? Q1 plus Q2 is also Q. So it's affine. I mean, so this set is called affine in the dual coordinate G if this range is also affine set. So basically, we want to achieve some. So basically, remember in the Pythagorean, Kullback-Leibler case, we have basically dual flat space. One is the M geodesic, right? M flat. The other one is G flat, E flat. So what do you mean by that? Well, these guys belongs to the exponential. So in terms of log transformation, they are all connected, right? But remember, because this log transformation is essentially comes from what? Sorry. Comes from here. I mean, comes from yeah, I guess here, right? In the Kullback-Leibler case, basically dual coordinate is complete simply log density, and so that's why E flat is considered. Okay.
So one is just constant, so we drop it.
So we now going to generalize it for general G.
Derivative is 1 plus rho cube, but this one is just constant, we drop it.
Right. So right, one that make no difference, right? Just constant. Okay, so basically, we want to create a flat with respect to this transformation. Okay, so that is the main thing. So how you want to characterize it? Basically, see, okay, 3-point. So if you look at the 3-point identity, say this guy, it belongs to M flat. Okay, that means that P and Q satisfy the same moment. Okay, say that EP TX is EQ TX, right?
We come again for only exponential family case.
No, we are talking about Bregman divergence now.
But what is TX then?
What do you mean by T? You mean delta?
When we define M flat, we have to say expectation of TX is equal reduced to P and Q, but
You mean what is the TX?
yeah,
Okay. So suppose you have a okay. So okay, that's good question. Okay. So when you say M flat, so I mean affine. So what do you mean by affine, right? So affine in terms of a certain subsistence statistic.
TX is given.
Okay, right. That's good. Yeah, right. So it can be anything, right? But suppose we need to consider a dual flat space. So that means one flat space should be defined through moment, right? So one flat space is defined through the moment function. So which is can be something like this. Okay. Now then, remember actually the whole idea in Pythagorean theorem for the Kullback-Leibler divergence is to show that this guy is a log Q. This guy is a log P, log R. And then this guy are actually E flat. Remember, right? Q and R are E flat at that time. So that this E flat and M flat are orthogonal. So that is basically the core of the idea when we prove it. And now, in general, then what it should be? Well, it should be flat in terms of delta G. So basically, this guy, the difference of this guy and this guy is a linear with respect to Tx. Okay. Then why will make the why this is so basically this one is kind of delta G flat some sense. Okay. And then this inner product is essentially doing the integration with respect to P minus Q. So basically this guy will be something like lambda t lambda prime tx times px minus qx d mu x. Okay, right? And then because these p and q belong to the m flat, this is 0. Okay, so that is the whole idea. We want to create a dually flat space, and then in statistics, what is most a common flat space is this kind of a M flat space. Okay, and then what would be a property? Because given the constraint, right? Given the M flat constraint, we need to determine the path or solution path that satisfy orthogonality with respect to the Bregman divergence measure, right? I mean, in terms of the Bregman divergence measure, G, generator G. So basically this is the condition, the solution path. So basically this gives you a solution path. That is basically the key idea. So and then of course here, when we talk about projection, we are talking about a flat space in some sense, right? So then this Q is a closed, well, projection itself doesn't have to be flat, but the Pythagorean theorem requires flatness. Okay, so this projection itself, Q doesn't have to be flat. It's just the closed and convex. That's it. But we need a affine set in the dual coordinate. Then we have equality, orthogonality, and equality. Okay. So that is basically a key idea. So see, remember this 3-point identity. We have this the cross product term, and we want to make this cross product term to be equal to 0. So what should we do? Well, this is okay. So we first identify the mapping. Okay, using the this is a dual coordinate system. So this is the dual coordinate system characterized by generator G, right? And then we can actually create a space, dual space, because we have a dual mapping, and we now have a dual space, and because Q is affine, then Y is also affine. Okay, and then construct a convex conjugate function. And then see this guy. So because of the duality, we have a we have an equality, right? Q over P. So dgp bar Q is equal to df Q bar P, right? And then this guy is what? FQ minus FP minus, well, actually, sorry, there's a dual. And so we need the dual mapping, not just the, so P and Q is in the original mapping coordinate system, but we need to use the dual. So that means we have a Y. So I think over, so what is fixed? PQ, Q, yeah, P and Q, and we Q OP, right? Over Q, sorry, I should have put Q in the set of capital Q. Okay, then because of this, okay, then we, so that means P is fixed. So only Q changes. Okay, so P is small p is fixed. So then because of this mapping, this is Y given Y corresponding P. So this is YQ essentially, right? I mean, if you use this, so, or even we can write it as a Y and delta G P. So that's probably better. I mean, inverse delta. And then this guy is Fy minus F of delta GP minus inner product of delta, okay, inner product of delta F of delta GP and Y.
And the Y minus delta.
Y minus, right, Y minus, right. So Y minus delta G, right. Thank you. Right. Okay. And then this guy is P because of the definition of the convex conjugate function. Okay. So that means this is constant. So that then we want to minimize this guy with respect to Y, turns out to be Fy minus integral, I mean the cross this guy. So that is why we get this one problem. Okay. Yeah. So P and Y minus delta GP. And then basically now this one we use okay. So we want to minimize this guy over Y, and then we know that solution Y star will satisfy. So basically, the solution Y star will satisfy this because this is this is the first guy is a delta phi y star. Okay, it's orthogonal. Okay. Well, we'll see more later or next week with more example. Then it will be more clear. And then basically this is using some Legendre duality. This is equivalent to this one. Okay. So let's move on to empirical like the example. So this is our generator. So in the empirical likelihood, we just assume that distribution is concentrated on the point mass. So basically this omega 1 to omega n characterize the distribution, right? And so if you use this as a generator, this is strictly convex. And we have this constraint, of course. And then use that to construct the Bregman divergence. So basically, we use this nu, right? Minus delta nu and w minus nu. Okay, and then what is delta? Reverse delta nu. Well, so what is the differentiation, right? So this guy. So this is what 1 over omega 1. So that means 1 over nu I. And so this one will be this one, right? Because of the property of log. And then this guy is essentially this guy, right? Because the measure is a discrete measure in the sample. Okay, and that turns out to be something called Itakura Saito. So they are two different person, right? That's not the two person in Japanese work together. So Koshike told me that they are very famous mathematician in Japan. You have your wife? You can go. Okay. Yeah. And so and now, yeah. So how do you define how to make a flat? Basically, see this guy characterize the dual system, right? So dual coordinate system. So basically, you use originally you have a omega. So this is the original like a zeta system, right? So this is like a zeta original coordinate system, while this is dual, which is a inverse minus inverse. And then we basically want to make suppose we have a certain sufficient statistic. So this is a moment condition, right? And then we basically make a fine in terms of this z. So that way that means you're eventually the weight. So the form of the empirical like the weight subject to constraint will be something like this. Okay, because it's basically affine with respect to dual coordinate system, right? So you get this one, And then basically, and then you can actually check that Pythagorean theorem holds under the moment constraint. So now you impose a moment constraint, with respect to C, and so then you can actually check out that. So I think yeah. So this is the bottom line. I mean, it if when we work in the apps, generally it's more difficult, but when you have a concrete example, right, then it's more clear what do you mean by dual coordinate system and affine. So this is actually the basically weight, the parametric model, I mean parametric form of the weight function, right? And that wave function is a linear after affine linear function of the surface statistic in terms of the affine I mean the dual transformation. 일단지. And then basically you can check after some algebra, you can actually check that they are orthogonal. So see, this is the kind of a thing I like to emphasize. So basically, we want this guy to be orthogonal, right? And so how to do that? Well, you have a surface statistic, and this is a one. One is just the density normalization constant. And so this guy is equal to 0 because it's a density, right? And this guy is equal to 0 because of the moment condition, because P and Q star belongs to the same M flat model. So that means we achieve the orthogonality. That means we'll have this Pythagorean equality. Okay, I think that's all.